Welcome to the session on factor of safety in 3DEC. This is Jim Hazard, 3DEC Product Manager at ITASCA. Okay, as you know, the definition of factor of safety is essentially the load capacity over the acting load. So a larger factor of safety means it's safer, you have a higher capacity or a lower load, and lowers of factor of safety are more dangerous because you have either a high load or a low capacity. You can do a factor of safety analysis in 3DEC, and the way it works is it takes any model that you can create and then tries to solve it for a given set of properties and determines whether or not it's stable or unstable. It will solve multiple versions of the model with different properties, and by doing that, you can figure out the factor of safety. You may or may not be familiar with the limit equilibrium approach, which is a very common way that people use to determine factor of safety of slopes, especially. This is a little bit different. This is what is called the shear strength reduction technique. We certainly did not invent this. Many finite element and other programs use this approach. But again, what it essentially does is reduces the shear strength until you reach a barely stable state, and you can use the amount of reduction to determine what the factor of safety is. The advantage of the shear strength reduction technique is that you don't have to make any assumptions about the failure mechanism. It will just evolve according to the mechanics of the problem. You can also get extra information out of the models like displacements and so on that you can't get from limit equilibrium. The downside, of course, is that it will be slower because we are running multiple models here as opposed to limit equilibrium, which is much quicker. So how do you reduce the shear strength? In general, I mean, the basic version of this is a more Coulomb type of material. And so you simply reduce the cohesion and the friction coefficient by some factor. So this bottom plot shows you the general way that this is done. Imagine you have some sort of more Coulomb failure envelope. This is plotted as shear stress versus normal stress. Your starting envelope is this green line. You reduce the cohesion, which reduces the intercept. You reduce the friction, which changes the angle. And you have a new failure envelope here, and you try to solve for that particular state. Note that you don't reduce the friction angle, you reduce the friction coefficient. It is possible to just reduce one or the other of these parameters. You can reduce just the cohesion, which is the top plot here, and that just causes the curve to shift to the right. Or you can reduce just the friction, which causes the curve to rotate. But almost always people are doing both at the same time. So the way that it works in 3DEC, or pretty much any shear strength reduction program, you will run a numerical simulation with some set of properties, and you will determine whether or not it's stable or whether it failed. You perform several simulations with different properties. Each time you reduce the strength by some trial value of the factor of safety. So, for example, the cohesion, the trial cohesion is the original cohesion divided by some number. And similarly, the trial friction angle, you can calculate it like this. Again, you don't just reduce the angle directly, you reduce the coefficient. And by looking at the value of this F, you can figure out the factor of safety. Essentially what you do is a binary search. So you start by reducing the strength by, say, a factor of 2, and you see if it's stable or not. And if it's unstable, then you reduce by a factor of 1.5 and try that and see if it's stable or not. If it's unstable, you reduce by a factor of 1.25 and so on. So you just do this binary search until you narrow in on the level of accuracy that you're interested in. So you can include or exclude different parameters when you're doing the factor of safety calculation. As I already mentioned, you could choose to use just the cohesion or just the friction. If you're using the ubiquitous joint model, you can include or exclude ubiquitous joint cohesion or ubiquitous joint friction. And in 3DEC, you have actual joints, and you can choose to include or exclude the joint friction and the joint cohesion. By default, these are all included. It is also possible to include the tension strength, but this is not included by default. If you have a hook-bound material, so this is a little bit more complicated because you don't have a cohesion and friction, but it is possible to convert the hook-bound strength in each zone to give an equivalent cohesion and friction. So you know what the confining stress is. You can fit a tangent to the hook-bound curve to get the cohesion and the friction. And that's basically what it does. And then it just reduces the cohesion and friction for each zone based on the equations that I showed before. For hook-bound or for more Coulomb, you should not use strain softening. You get some very weird effects if you have strain softening, because essentially the shear strength reduction approach is really just trying to tell you when something starts failing. The behavior after failure is not really important. And if you have things weakening after failure, you start to get some strange results. So anyway, that's how it works for hook-bound material. For other more sophisticated materials, if you're getting into some of the soils materials like cam clay and so on, the factor of safety does not work for those. Right now, it's working for more Coulomb, hook-bound, and ubiquitous joint. A relatively recent addition to the factor of safety capability is the ability to show contours of factor of safety. And we'll have an example of this in a minute, so it'll become more clear. But essentially what it does is it runs the simulation like regular and trying all these different strength values and running the model. After each one of the simulations, it stores the grid point velocity. And so then when you get to the end, you can use the stored velocities to give you sort of a map of factor of safety in different parts of the model. So you choose some sort of threshold velocity, and then all the grid points that have a velocity above that, for a given factor of safety will be shown, and then all the grid points that have a velocity below that for a given factor of safety, are not shown. So you can essentially get a map like shown here. You can imagine if you had a slope with multiple bumps in it, parts of this thing might be failing at a given factor of safety and parts of them might not. So you can use this to try to sort of delineate where your danger areas are, rather than just getting a global factor of safety for the whole system. And again, we'll show this in an example in a minute. Another thing I'll show in an example in a minute is calculating factor of safety by hand. So the built-in factor of safety calculation, again, does this binary search where it runs multiple simulations to try and narrow down the actual factor of safety. And this can end up with you running 7 or 8 models. In 2D, this is probably okay. If you have a humongous 3D model, this could take a very, very long time. So in 3D, you will often see people doing this by hand. Instead of allowing 3DEC to go through its binary search, you kind of instead gradually reduce the strength bit by bit until you get to the point where it's failing. And this can potentially speed things up when you're just trying to get to the factor of safety. And I'll show how to do that with fish in a minute. Okay, so let's run a couple of examples just to show you how this works. And hopefully that will be quite illuminating. So I'm going to start 3DEC. Now I've given you these examples in the material. Hopefully you have downloaded it. So I'm going to open an existing project. And I'm going to navigate my way to this training material. So there should be a directory called FOS. Inside of that, there are 2 subdirectories. We'll start with this second one, slope_FOS. Just open that project. All right, so I've given you a project here with 3 data files in it and 3 plots already set up. There's not much new here. Really, the point of this is just to show you how the factor of safety calculation works. So with the factor of safety calculation, you almost always want to run it with large strain off, because again, we're really only interested in the onset of failure. What happens after failure, slope run out, stuff like that is totally not important. And it can certainly produce some weird results. So almost always you want to turn the large strain off when you're doing factor of safety calculation. Here I'm creating a simple slope. In the past, we've created a slope by making a big block and cutting it out. In this case, I'm creating the slope by making defining the shape of the block with a prism, and then creating another block underneath it and then joining them together. So if we just run lines 1 to 10 here, so I selected them, I right click and I hit run selection. I go to the blocks plot. You can see here what I've got is 2 blocks. So the top one I just made with this prism command. The bottom one is just a regular old block. You can see this is really a 2-dimensional example. This was actually a UDEC example that we're running in 3DEC. The 2D, it's extruded by some amount, 1 meter, I think. If we run these pseudo 2D examples, they just go a lot faster. Okay, so we created the slope. Now we're cutting in a joint set. We've got a dip direction of 35 degrees. Sorry, a dip of 35 degrees, dip direction of 90, so it's dipping off to the right. Spacing of 20. The number here is not necessary. It will just fill up the given space with joints, and then you give a starting coordinate. After we cut the joints, we generate zones. So we have a spacing of 20, and we use a zone edge length of 10. In general, you probably want to have at least 2 zones across the diameter or across the dimension of each block. So again, we got 20 meter spacing. So at a maximum, you want to have 10 meter zones here. We're using more Coulomb material, standard properties. We're using more Coulomb for the joints. Standard properties here. The only thing that's interesting here is we're using a residual cohesion, which is the same as the peak cohesion. Remember in the joint section, we said that by default, the residual cohesion is 0. So these joints behave brittly. When you do these factor of safety analyses, again, you probably want to run them so that they're like perfectly plastic, because the stuff that happens after failure is not really important. So we set the residual cohesion for the joints to be the same as the peak cohesion. For the zones, the default is such that the residual is the same as the peak, so you don't need to specify. We fix the boundaries. We turn on gravity. Here we're using the whole vector, but recall you don't necessarily need to give the X, Y, and Z components. You could just type in 9.81 and it assumes you mean the gravity is acting downwards in the Z direction. This is probably a new command that we haven't shown yet. Block zone nodal mixed discretization on. What this does is it gives you more accurate plasticity results when you're using tetrahedral elements. As discussed in a previous session, 3DEC almost always is using tetrahedral zones because it's easy to fill up a volume with tens. It's much more difficult to fill up a volume with hexes. We know that tens are less accurate than hexes, especially when it comes to plasticity. There is a mathematical trick here that makes the tets more accurate and essentially does some averaging of stresses and or strains between the tets. And you can turn that on with this command, block zone nodal mixed discretization on. Almost always you should turn this on, especially if you have expecting to see plasticity in your zones. The only reason it's not on by default is that sometimes in some circumstances, you can have a tensile failure and a bit of instability because it's trying to average amongst all these zones. And you know, if one zone is failing in tension, then you can get this sort of positive feedback thing, and it causes instability at certain points. So occasionally that does happen when you turn on the nodal mixed discretization. Most of the time it doesn't. I would recommend turning this on most of the time. Okay, then we'd say model solve elastic. Remember this command, it turns everything elastic, solves it, then gives everything its true strength, solves it again, and then we save it. That's the initial state. We set the velocities back to 0, we set the displacements back to 0, and then all we do is give this command, model factor of safety. If I just give the command model factor of safety, it will work, and it will go along and create some default file names for you. If I want to give a specific file name, I can specify it here. So let's run this, and we'll talk about it some more as it's going, because it does take a little bit of time. Okay, so here it's doing the solve elastic part. It gets to the ratio of 1e minus 5, solves it again, saves it. Now it's actually doing the factor of safety part. So you can see here, hopefully you can see here what's happening. It's solving some initial stable state. So that's with a factor of safety of 1. And then it tries a factor of safety of 2. So it essentially reduces the cohesion and the friction coefficient by a factor of 2 and sees if it's stable or not. It turns out that it's not stable. So now we know the stable state is 1. We know the unstable state is 2. It's now testing 1.5, right? It's doing this binary search. So it tests the 1.5 state. That turns out to be unstable as well. So now the unstable state is 1.5. Oh, it did the 1.25. It solved that quite quickly. That's the stable state. Now it's in between these two, 1.375, and so on. You see how it's progressing. You'll see in the project pane, it's creating some files for you automatically. There's the initial state, the current best guess at a stable state, and the current best guess at an unstable state. It keeps on overwriting these until you get to the end, when it narrows in on some tolerance here. I think by default, the tolerance is 0.005. You can change that with a keyword if you don't want to run so many models here. Often you might want to, not necessarily be quite so accurate with the factor of safety. But by default, it's 0.005. So this will keep running until it narrows in on a factor of safety. And when it's done, you'll have the initial state saved, this just stable state saved, and the just unstable state saved. So here it's done. It's telling you the factor of safety is 1.36, which is great. I go back to my block plot. The plot that I've given you in the example, it defaults to showing you the state. Now look, this is actually the initial state, so this is not very interesting. It gets much more interesting when I go to show the unstable state. So I can double click on that. Here we go. So now you can see a whole bunch of these zones are actually failing. Maybe we don't care about the ones failing in the past. Remember this trick. If I click on block state plot item, under the attributes, I can click on no past. So these are only the zones that are failing now. A lot of them in tension, some of them in shear. You can see the arrows indicating the movement. This is really suggesting that there's probably movement occurring on the joints. If I go and look at the joints, here's a plot that I've given you. This is showing shear displacement on the joints. Let's hide the arrows. Right, this is a contour of shear displacement. You can see this particular joint here is really where all the action is. There's some pretty severe sliding on this particular joint here, which is generally what is controlling the stability of this slope. Often when people are doing these analyses, you want to see the failure surface. In this case, we kind of know the failure surface is, corresponds to this joint plane. If it was more of a continuum type model, what you would plot you can go over here and change the label to contour and show displacements. It's reasonably obvious where the failure surface is here. You could show velocities. Again, pretty obvious. If it was more of a continuum type model, what people often plot is strain, increment, and maximum shear strain. And you can smooth this out a little bit by choosing volumetric averaging for the plotting. So again, it's the joint that's really controlling things here. In a continuum type model, you'd see a nice failure surface with this contour. Here you can see some of the shearing and then some sort of a probably tensile crack here. But this is a useful plot item if you're if it's controlled by the failure of the zones rather than the failure of the joint. Okay, so that's it. I mean, running a factor of safety analysis, the default way that 3DEC gives you is very simple. What I will show now is how you might go about calculating this by hand. You can see that this pseudo 2D model ran quite quickly. It only took 5 minutes or something. You could imagine a real 3D model is going to take a lot longer than this. What people will do, I've got a file here called by hand. You can look at it. I'm assuming that you've already viewed the fish introduction to fish session. So I'll just walk you through the way you could do this. So here we're looping through all the zones. We're storing the initial cohesion and the initial friction in an extra variable. So recall I briefly mentioned in the fish section that every zone, every grid point, every contact, every subcontact, you can store extra data. Up to 128 things, whatever you want. They can be floating point numbers, they can be strings, they can be tensors, it doesn't matter. In this case, we're going to store the cohesion in extra variable number 1 and the friction in extra variable number 2. And same with the subcontacts, we're storing cohesion and friction in the extra variables. We call this function by using the square brackets here. Now, we need some way of determining whether or not the model is stable. And so what we're going to do is just measure the maximum displacement of any point in the model. So we're assuming that as we go along weakening this thing, the maximum displacement will be relatively small, relatively small, relatively small, until some point when the slope really starts to fail, and then you're going to see a dramatic increase in the maximum displacement. So if we plot this maximum displacement versus the amount of weakening, there should be an elbow in the curve, and it will indicate to us, where the factor of safety is, where it really goes from stable to unstable. And so our criteria for that is just the maximum displacement in the model. So all we do here is loop through all of the grid points and store the maximum displacement. And then we have a function that just runs it. So we're going to store that maximum displacement versus factor of safety in a table. We didn't talk about tables yet, but you can certainly read about that in the manual. And what a table is just a set of XY pairs. They could be anything. In this case, X is factor of safety, Y is maximum displacement. When you have a table, you can then plot a table, just like you do with the histories, and I'll show how that works in a minute. So we'll start with a factor of safety of 1. We're going to loop as many tests as you want, but in this case, I'm just doing 8. I should set this running while we're speaking so that it can be finished by the time we're done. We're looping through 8 times. Each time through the loop, we're incrementing the factor of safety. So we start with 1. Then first time through, we're going to try 1.05. We reduce the cohesion by that factor. So we take the original cohesion that we stored, which is in the extra variable, divide by this factor of safety, which is 1.05, and set the cohesion to be that. The friction is slightly more complicated because remember, you need to reduce by the friction coefficient, not the friction angle. So we calculate the friction coefficient from the stored value, we reduce by this factor, and then we turn it back into an angle and set it as a zone property. Exactly the same thing with the subcontacts. We reduce the cohesion by the factor. We reduce the friction coefficient by the factor. And we get on here and we solve. This thing might not solve, right? The whole point of this is that we're trying to find the boundary between stable and unstable. So we say model solve to the default ratio of 1e minus 5, but it might not solve. So we'll say if it hasn't solved in 20,000 cycles, then stop running and carry on. After the solve, we store the factor of safety and the maximum displacement in the table. So again, the table is XY pairs. So we just make a vector here. The X is a factor of safety, which is this variable up here. First time through is 1.05. The second variable is max displacement. If I just type max underscore displacement here, it will automatically call this function, do the calculation, and return this value. Plops that into the table. Save the state. I can calculate a file name from the factor of safety, and it's going to save the state, and it's going to loop through again. And now this is already done. You can see over here on the left that it's saved a state for 105, 110, 115, 120, and so on, up to 140. So I'm sitting at my 140 state. I can see here by looking at the console that this did not solve, right? The mechanical ratio is 4.7 e minus 5, which is bigger than 1 e minus 5. It ran 20,000 cycles, which was the limit I specified. So we know for sure, well, probably for sure, this factor of safety of 1.4 is not stable. Now we want to look at our graph or our table to see if we can pick off where the actual factor of safety is. So I've given you this table plot. Wanted to generate this cell. I'll show you how this is generated. You know what? Let's just make a new one just so I can show you how it's done. Make a new plot. Call it table 2. I go to plus. Your charts, one of the choices is table chart. I've only got one table here, factor of safety. Okay, it draws a line according to these XY pairs. In this particular case, it's nice to see the points on the line. So if I go over to series, where it says style line, I can change it to both a line and a mark. By default, the mark is a plus of size 2. It's a little bit hard to see. Let's make it bigger. Let's make it 4. And let's change the color of these things too. It's also a little hard to see. Let's make them both dark blue. Right, so you can see the maximum, and I can change the axes here to make it a little bit clearer what I'm looking at. I can change the title. So axis 1, let's make the label FOS. And for axis 2, let's make the label max disp meters. It defaults to this sort of scientific notation, which is, in this particular case, maybe not necessary. So I can go over here to my attributes, and where it says exponent, I can expand that and uncheck auto and change the exponent to be 0 instead of 1. And now it's showing me the displacement in actual meters instead of times 10 to the 1. So, okay, what you can see here is that from 1.05 to 1.35, there's not a lot of displacement. And then at 1.4, catastrophe, right? So the real factor of safety is somewhere between 1.35 and 1.4. We could try and zoom in on this a little bit by changing the scale. I go to axis 2, default maximum is 16. If we make the default maximum something like 2, well, let's make it even smaller. Let's make it 1. So now you can see that, you know, at 1.3, it's moving a little bit. At 1.35, it's moving a little bit more. And again, after that, it's catastrophe. So, you know, from running the actual factor of safety calculation 10 minutes ago, that the real value was 1.36. If you wanted to narrow this down, we know here that it's somewhere between 1.35 and 4. You could go through, restore the 1.35 case, go back here, change your tolerance, run this loop again and make this instead 0.01, and see if you can narrow it down. That's what I would do. Again, be aware, this is kind of a fast way to get to a rough idea of the factor of safety. It's not 100% correct because the path is different. You're sort of gradually weakening something and gradually weakening something. In the true factor of safety analysis, you go back to the beginning and then weaken it, and then go back to the beginning and then weaken it, and go back to the beginning and weaken it. So the path is a little bit different, but in general, I found that this actually works pretty well. It gives you something quite close to the same answer. One more thing to show before we move on here. This is this sort of old-fashioned way of running these loops. You can do all of this, almost all of this multi-threaded, and it would be faster. In this particular case, it doesn't really matter that much because most of these functions were only executing once, or, in this case, after every solve. Multi-threading is useful if you're, executing something every step or every 10 steps. Not probably that useful in this case, but just to show you how it's done. Again, I've given you this file, and I'll just quickly show it here. If you click on multithreaded.dat. The way you would do this multi-threaded is instead of fish define, you say fish operator, and you have to send it a parameter, which is a zone pointer. This is exactly the same as we just saw without the loop and the end loop. So you take the exact same function, you change define to operator, you send it the zone pointer, you get rid of the loop and the end loop, and when you call it, you send it the whole list. And it intelligently splits up this list onto different processors and runs this thing a bunch of times simultaneously. Same thing with the subcontacts. You send it the whole subcontact list, and it runs in a multi-threaded way. With the maximum displacement, this is slightly more confusing syntax here, but what this is essentially doing is calculating the maximum displacement of all the grid points in a multi-threaded way. Same thing for weakening the zones. So again, we're going to get rid of the loop here and just send it the zone pointer and the factor of safety as a second parameter. It will do the weakening. This is exactly the same code you saw before, just without the loop and the end loop. Same with the subcontacts. And then down here, we call it like this. We call this function, we send it the whole list, with the second parameter being the factor of safety. We call it subcontact function, we send it the whole subcontact list and the factor of safety. And it does this weakening in a multi-threaded way. Otherwise, it does exactly the same thing, and you end up with exactly the same answer. Theoretically, it goes a little bit faster. In this particular case, it's probably not noticeable. Okay, that's all I'm going to say about this example. One more example to show, which is that factor safety contour example. So I'm going to open a project. Let's go up to the factor of safety contours directory and open the project inside of there. Okay, this example is right out of the manual, but just to talk through it. Again, we create the slope, in this case, with a bunch of prisms and join them together. If we just run lines 1 to 17 here. We can click on one of these plots, FOS. So you can see what we've done here is created multiple blocks of different shapes and join them together. Point of this example is to use it because we've got a slope with a bump in it. There's potentially different factors of safety for different parts of this slope. This is basically a continuum model. And again, it's basically a 2D model. To make it run faster, there's no joints in this thing. But of course, the same procedure works if you have joints. Okay, so we make the blocks, we zone it. This is using the new zoning logic that we talked about. So we specify the zone sizes. We specify a zone edge length of 0.5 in the top part of the slope. And then we say generate new with a minimum edge of 0.5 and a maximum edge of 2. So you'll have smaller zones near the top and bigger zones near the bottom. Again, more Coulomb material. In this case, we're giving it essentially an infinite tension strength. We don't want to see failure in tension. There's no joints. We don't even need the joint properties here. Again, boundary conditions, fixing the bottom and the sides. Turning on gravity, using this nodal mixed discretization on again. You know what, I should run this while I'm speaking so that it will be done by the time we're done speaking. Turning on this nodal mixed discretization again, which we talked about before. In this case, it's especially important because there are no joints. There's a lot of tets. All the failure that we're going to observe here is related to the plasticity of the tets. So you definitely want to do this in this case. Model solve, elastic. We've seen this before. The only difference here is now instead of using the default ratio of 1e minus 5, I'm using 1e minus 6. This just gives you a more accurate answer to get to the equilibrium state. Set the velocity to 0. We set the displacement to 0. We run model factor of safety. I did not give a file name, so it uses a default file name of just FOS. And again, it comes up with these 3 states: the initial state, the stable state, and the unstable state. Let's just look at the unstable state here. Let's make a new plot. I've given you some plots here, but let's just click on FOS. Now let's make a new plot just so I can show you how it's done. So I make a new plot. Let's call it FOS2. We can add the blocks. Right, so you can see how the zoning is smaller at the top. I could contour if I choose contour, it defaults to displacement. So you can see this part of the slope is doing a lot of displacement. This part, not so much. Remember before, especially in these continuum type models, you can get an idea of where the failure surface is by plotting strain. In 3DEC and the other ITASCA programs, the strain is called the strain increment, but this is really just the strain. I can choose maximum shear as a component. I can choose volumetric averaging to smooth this plot out a little bit. So here you get a good view of the failure surface and a hint of a failure surface up here as well. So there's 2 components of failure of this slope. And again, the point of this exercise was to plot these factor of safety contours. We can probably guess that this bottom part is less safe than the top part here. And we can sort of quantify that by looking at these factor of safety contours. So over here where it says contour, I can change the value to factor of safety. So this doesn't look like much. What it's doing is it's looking at the velocities of the grid points that it saves each time through the factor of safety calculation and comparing it against some threshold. And again, if it's above the threshold, it's considered failed at that factor of safety. And if it's below the threshold, it's considered not failed at that factor of safety. This threshold is probably way too big for our model. So let's get rid of a couple zeros here. This is looking a little bit more sensible. Probably we don't need this total range of factor of safety. We don't care about the stuff that has a factor of safety of 2. So let's make the maximum contour 1, let's say. So we can see that everything here that's blue, assuming that this velocity limit demarcates the boundary between stable and unstable, everything that's blue here has a factor of safety of 1.25 or less. And when we're running a factor of safety of 1.25, all of these grid points have a velocity faster than this 0.01. Similarly, all of these green guys, when the factor of safety is 1.5, they have a velocity faster than 0.01. So for a factor of safety of 1.5, you can consider this part to be unstable. For a factor of safety of 1.25, you can consider this part to be unstable, and so on. we can try to narrow this in a little bit more. Let's change our velocity limit to be something even faster. Right, so if we choose 0.1, now it's really obvious. This part here is the most unstable part. It's blue, and this part up here is not quite as unstable, based on the velocities. Yeah, the plot that I've given you, it uses different. Oh, that's not very interesting. The only difference here is that it's using a different interval for the contours, so it looks a little bit more blocky than the one that we just built. So this is potentially useful. One last thing to show you here, which I forgot to show you in the previous example, you can actually put the factor of safety on the plot. So if I go to the plus, the global factor of safety, I should say, if I go to the plus under miscellaneous, there's a factor of safety plot item. If I double click on that, it just puts it down here in the legend. The global factor of safety that it calculated was 1.39 for the whole slope. There you go. And so again, this factor of safety contour plot is potentially informative because this just tells you the global factor of safety of the whole thing, but there might be different pieces that are more or less stable than that. Okay, that is the end of the factor of safety session. Thank you for watching.